first talk is going to be Peter Sarnak, who's going to tell us about matrix moment problem and how it functions.
Thank you. So this doesn't quite fit in terms of hyperbolic polynomials, although real rootedness is very much something that we're interested in for the Riemann zeta function that I'll remind you about in a second. I guess given the audience, I should make clear what I'm talking about, which I will explain in a second. All of what I describe here is joint with Michael Rubinstein. We've been working on this sort of thing for years. He's perhaps more than anyone in the world able to compute zeros of L functions far further than anyone else. It used to be on Lützko. Rubinstein has taken over, and for many years we've been trying to understand the computational complexity of this question. And as you will see, we've got to some point, I think. All right, so let me frighten you with some slide there, which I'll explain now what I'm talking about in a very down-to-earth and most important case. And then I'll return to that and then explicate the entire discussion for just elliptic curves, because that's got all the beef and it's got all the interest. So the problem we're interested in is we have some kind of zeta function like the Riemann zeta function and its generalizations. So it's got a product over primes or a series representation. And as you probably know, this function has an analytic continuation and functional equation that coming from the additive structure, and because of this product over primes, which is equivalent to unique factorization, it marries the primes and this analytic function in a quite deep way. And Riemann, and I want to explain this point, Riemann showed that if you take pi to the minus s over 2, gamma s over 2, times the Riemann zeta function, which I always call lambda of s. This will be a generalization there. If you append these elementary functions, a gamma function and this exponential function, then he proved a very famous functional equation, which relates lambda of 1 minus s to lambda of s, and simultaneously analytically continuing this function, it's of the form 1 over s. It's got a pole 1 over s minus 1 plus this. Got s minus 1, 1 over s plus something which is rapidly convergent in the plane, in any vertical strip in the plane. And so this looks like, so both this, I won't write down his formula, this allowed him to analytically continue, get this functional equation, and make this very famous Riemann hypothesis, which he needed for certain purposes. It's not so well known that Riemann himself, before making this conjecture, computed a few zeros. And in order to compute zeros, he had to overcome a great difficult point, which is going to be the center of this lecture. He sort of discovered all the key analytic aspects of this. And the point is this, that if we're on the line, so all the zeros of this completed function are supposed to be on the line a half. The first zeros he computed himself roughly at a half plus I times 14 something, point something. So it's quite high up, symmetric. And then he computed the first three. I'll get back to this in a second. And why is this such a difficult problem, especially if the first zero is so high, is that the formula that you have, and all formulae that naive formulae that you have for this function, have a gamma function there. And the gamma function decays exponentially, like e to the minus pi over 2 times the absolute value of t when t gets large. This is just Stirling's formula. So if you Riemann and all you have is a pencil and paper and you want to compute that the first zero is on the line a half, he didn't make this conjecture, as I say, in a vacuum. The way he would check it, and the way he did check it, is you do a contour integral of zeta primed over zeta around here. Once you have an expression, once you can compute zeta sufficiently accurately to compute the integral 1 over 2 pi, the integral of zeta primed over zeta over this contour, and you count how many zeros there are. You get a number, and because it's an integer, the count, if you are If you get a number which is close to 1, then there's exactly 1 0. And then by the functional equation, that 0 has to be on the line half if there's 1 0 in that. And people have gone very high up. As I say, the first 0 is so high that e to the minus pi over 2 times 14 is a tiny number for a guy working with a pencil and paper. So he had to find a different way to understand this. And he did it. It's in his Nachlass. Nobody noticed this. This Nachlass, people looked at it, like Hilbert, many other people couldn't understand what's in the Nachlass until Carl Ludwig Siegel came along. And he understood in these pages what Riemann was doing, and that he'd computed the first few zeros to about 10 decimal places. And I will call this the Riemann-Siegel formula because Siegel explained it. And it's going to be the gold standard for computation. And what Riemann's method shows is by changing with weights, he's able to show that you can write zeta at height t. So I suppose I'm interested in the complexity. I'm a half plus it. T is a very big number, maybe 10 to the 20. And I'm at height t. He discovers you can write the Riemann zeta function as a series of length, roughly square root of the conductor. The conductor here will be t, square root of t terms. And that's the gold standard. He found that you could compute the zeros in that speed, square root of height t. So he could get this guy at 14. And if you look at any tables or any data on the web, you'll see nobody can really get much more than 10 to the 20 or 10 to the 23 because the square root of that is roughly the number of operations you'll have to do to get zeros. So let's go, for example, computed the 10 to the 20th zero and its 70 million neighbors. He didn't compute all the zeros up to 10 to the 20, and he did some interesting things with that. All right, so that's the Riemann zeta function, and I've mentioned this formula, which I didn't explain. And the general setting is you have a generalization of this, where there'll be coefficients here, and there'll be a product here with coefficients there. And the cases I'll be interested in come from algebraic geometry. I'll show you in a second. So the local factors will be coming from looking at some variety mod P. And the big theorem is a big conjecture, which is known in many cases, is certain L functions, which generalize the Riemann zeta function, have analytic continuations and functional equations. And there's a number, so I'll be interested in computing the zeros of such an L function, not high up, but rather low down, mainly at the central point. So the central point 1/2 turns out always to be the most interesting in these more general L functions, which are self-dual. And there's a very important number. This entire talk is going to be about this root number, which is a plus or minus 1, which says the functional equation goes from s into 1 minus s. And there's a conductor, which is, I said square root t there, which is called n of pi, which when you have an object like this, and I'm going to explicate one in a minute, so don't panic, this conductor is measuring ramification. And this whole problem that I'm interested in here is to try and understand the complexity of ramification. And I'll be assuming anything I want, specifically the Riemann hypothesis as I go along, or any other conjectures. Because the proof of the pudding, and I'm going to show you algorithms, is if they run and they assume some conjectures and they run, then the proof of the pudding is whether they run, nothing else. Okay, so there is to any automorphic form, whatever that is, an integer which measures ramification, and it measures the complexity of computing zeros. And we won't be talking about zeros high up. We'll be talking about zeros especially near the point 1/2 or at 1/2. All right, so let me explicate this. And this is the only example you need to think about. And even this will quickly be replaced by a purely polynomial model problem, which the main problem reduces to. All right, so you have an elliptic curve, which I put in Weierstrass form. I'm working of the integers, so I don't even continue to put it in the simplest form. So it's y squared equals a cubic, and there's some other terms, and their coefficients. And given this global elliptic curve, defined over the integers or over the rationals, if you wish, and you form these standard invariants. Don't look at them too carefully. The most important thing is the discriminant, which is the discriminant of the cubic. And I'm given an elliptic curve like this, and I'll make some assumptions about the coefficients. They're minor, the relatively prime conditions about the C4, that polynomial there, and C6. And if this is not true, you can get around that without too much difficulty. And the issue is that when I take this elliptic curve and I reduce it mod p and I look at the number of solutions over the finite field with p elements, which is, so the name of the game in this whole talk is I'm going to be able to, my idea is I'm going to compute this elliptic curve mod p for many small p's. P may go up to log of the conductor, or maybe the conductor to the half. And the assumption is I can, and I'll show you that's a theorem, that you can compute the local factors very quickly in logarithm number of steps. So you compute these numbers, and that are numbers that you can have in your hands. And now you want to be able to say something about the zeros or about the root number of this elliptic curve by computing small numbers. So that's a complexity question. All right, so the two key numbers are the conductor of this. The conductor, let me assume the conductor is square free. That's an issue, but one that's not so serious. So I'll assume the discriminant, in fact, is square free, and I'll assume these other minor things here. Then the root number, and this is the most important thing for us here. The root number of this elliptic curve, the sign of the functional equation, depends on some Legendre symbol. Now, a Legendre symbol, AB, or Jacobi symbol, is something you can compute in logarithm number of logarithm.
Can you say one more time, what's the root number? I don't see
the
it.
root is the number is the sign of the functional equation of the L function. So the L function of the elliptic curve will be a series and a product. And the root number is the sign of the functional equation, global sign of the functional equation of the L function of this elliptic curve. And that global root number is gotten by computing over all primes which divide the conductor. All come from ramification. So if you want to compute the root number, you more or less, as far as we know, have to factor the conductor.
Plus or minus 1. That's
It's just a sign. It's just a parity, and it's the most, as I will explain, the biggest secret kept by a number, the number of prime factors. Yeah?
Why
Yes,
is it called
ask.
the conductor?
What?
Why is it called the conductor? Is it
That's a good question. Actually, I don't know. It comes back to Dirichlet. If you have a Dirichlet L function with period Q, the conductor is what we call it. There may be other reasons that the actual word conductor, but it's the most important thing. It's the product of the number, the places at which this object has bad reduction.
Oh, you find it in German. Oh, it's very Fluber.
Probably right. Probably comes from German. Yeah. Anyway, it's the most important number, and this number is also very important. So the sign and the global conductor. Now, the root number is essentially this Legendre symbol. This Legendre symbol is something you can compute quickly. So if I give you a Legendre symbol AB, it's a plus or minus 1. There's a reciprocity of Gauss that says AB is BA times something explicit. So you can just repeatedly halve the size of the numbers, and that's a logarithm number of steps, just like Euclid's algorithm, to get that. So this is not going to be difficult to compute. But this is a beautiful number, and that's the number I'm really interested in understanding. It's essentially the root number, especially as far as computation goes. So the root number and this Mobius function, the Mobius function is the parity of the number of prime factors of a number. Say it's square free, as I'm assuming here. And we don't know how to compute that quickly without factoring. And my belief is they are the same complexity. And that's the problem I'm trying to understand. Can we compute this number quickly? Now, if you work with elliptic curves or any of these L functions, you're really eager to understand the order of vanishing of the L function of this elliptic curve at the center, because there's a famous conjecture called the Birch-Swinnerton-Dyer conjecture, which gives you the rank of the elliptic curve in terms of the order of vanishing. So the parity of the order of vanishing, I'm assuming all these conjectures, the parity would be given by the root number. The order of vanishing is something that we're really interested to understand, and the number of steps we need to compute the root number, well, that I'll discuss in a second, but by Riemann's gold standard, it takes square root of the conductor steps to compute all these things. And if you don't use L functions, if you think you're going to compute the number of solutions to the Diophantine equation, the rank is the number of rational points, the rank of the group of rational points. Well, the solutions are so big you'll never see them, so there is no other way to compute things quickly. So these global L functions carry tightly the information all built into the conductor. All right, so just again, for this elliptic curve case, there are local factors which, when I multiply out, will give lambda and e. I'll have a series representation or a product representation for this global L function of the elliptic curve. And there's a beautiful theorem of Scove using a little bit of algebraic geometry to compute the number of points. So you give an elliptic curve in the form that I gave it to you. Now I say, how many points has got mod p, where p is a prime? It may be that p divides the conductor. It's got bad reduction, but for this lecture, you should think of the conductor as being a massive number, 10 to the 200, and all its prime factors are bigger than 10 to the 100. And I'm computing these coefficients. How many solutions are there to this elliptic curve mod p, where p is small, maybe going up to conductor to a small power, or maybe going up to log of the conductor. And so the question is, can you compute the number of solutions to that equation over a finite field quickly? And Scove, I think he was a student of Lenstra, maybe even, I don't know if it was here at Berkeley, but anyway, René Scove has an amazing algorithm which has been implemented, which computes the number AP, which is, there's only one number in the elliptic curve case. There's one number here that you, when you unramify that, one number that you have to put here in a quadratic polynomial. And it's the Frobenius of the elliptic curve, mod p. And that number he computes in polylog p steps. It's log p to the 6 steps. So you can compute the coefficients quickly. And so the problem we're trying to understand is, if you can compute the coefficients quickly, can you compute something about the zeros of the L function? And let me go back to the Riemann story, the gold standard, I call it. If for the Riemann formula, I said he writes down the value of zeta at height t in terms of two series whose lengths are roughly square root of the conductor in length each. And that's why you can compute the value very quickly. But those two series depend on knowing the root number. So you do need to know the root number, and that's important because this whole lecture is about trying to determine the root number with very little data. So you do need to know the root number, and if you do, then this Riemann-Siegel formula allows you to compute anything I want in square root of the conductor plus little o1 steps. So that's the gold standard, and that's a standard we are eager to beat. And I repeat that the global root number is a product over all primes of some local things that you can compute. And so we don't know any way of computing this without first factoring the conductor. The other thing that Riemann allows you to compute, and this is going to be what we're going to be setting our goals at, is I'm assuming Riemann, the Riemann hypothesis that is, for this L function. Anything that comes along like this. And you could ask, how many zeros are there on the line a half up to height t? So I'm asking, how many zeros are there of the L function? They're all supposed to be on the line a half between 0 and t. And I call that SET. And of course, Riemann's method allows you to compute that in square root of the conductor steps. Okay, and that's an exact count of the number of zeros of the L function. So the gold standard is square root, and the big question is, can you do better? Can you do something sub-exponential, or maybe you can get something that's polynomial? And I want to explain why this is of such interest to us. Is the parity of a number, the Mobius, is where everything breaks down. In sieve theory, there's something called the parity principle. It stops us doing everything we're trying to do. It's very difficult analytically to tell whether a number's got an odd or an even number of prime factors. It's the last secret that the number keeps. If you're interested in machine learning, I was wondering, try to teach a machine to guess what mu of n is for large n with any probability of doing better than just flipping a coin. I don't think you'll learn anything. I have conjectures about the randomness in Mobius, and it's a fundamental thing theoretically. It's also a fundamental thing in terms of factoring. So I'm saying, I don't have a proof of this, but it looks like it's probably true, that factoring and computing mu are in the same complexity class. Well, secretly, I believe factoring is easy anyway, so all of these things are easy, but I guess mankind likes to think, or your security systems like to pretend it's hard. And in fact, this is one of the reasons I'm very interested in this, is maybe I could do something that's going better than the best factoring algorithms to compute the root number. That's our aim here. Can we do better than that? So the benchmarks for this problem are sub-exponential, and the next benchmark would be how sub-exponential compared to where all factoring algorithms bottleneck. The number field sieve, for example. All right. So the theorem, that's what I want to announce here, is that we can compute the root number and we can compute this counting function for any elliptic curve in sub-exponential time. So, but we can't compute the rank. I can compute the counting function for some t's, not every t. I don't know which t's. The t's come in the algorithm and they allow me to compute exactly how many zeros are there up to some values of t, many values of t, but not t's that I can choose a priori. And the root number I can always compute sub-exponentially, and I'm already computing with the best factoring algorithms without ever factoring the integer. So this is measuring, this really is exploiting this to try and understand. So this is what we're trying to do. We're trying to compute this root number. It might have 7 prime factors, the Mobius. The conductor is extremely large, and I'm computing the number of solutions mod p for very small p's. And I'm telling you up to square root or n to the epsilon, that's what sub-exponential is. And I can tell you what the sign is without ever factoring, and I'm bottlenecking roughly at the same place as factoring. So I'm, of course, hoping this would completely smash open factoring, but there's going to be a caveat at the end of the lecture. All right, so that's our main theorem. I'll explain it a little bit. We're assuming GRH throughout, so algorithms work, so that's not an issue. Riemann is true. You don't need to worry about that in this world. I'm assuming other conjectures along the way because I'm going to bring in random matrix theory in its strongest form. So I'm assuming conjectures of Katz and myself, which tell you about the distributions of zeros of L functions as you vary in this kind of range, or as you vary over families and its connection to random matrix theory. But those conjectures are only used in convincing me and you that the algorithm terminates quickly. The answer, when it feeds out an answer that the root number is 1 or minus 1, is correct. It's the running time that depends on these conjectures. And incidentally, all the number field sieves and all those, nothing is proved there. Those all depend on heuristics that people just assume are true as they go along. And again, the proof of anything is in the pudding. If they can factor a big number, you don't argue.
So Peter, so then you're saying that you're trying to compute the root number without factoring?
Absolutely.
And assuming all of these conjectures, you can match the running time of the best factoring algorithm?
They're all sub-exponential, and the power in the sub-exponential I haven't quite understood. I'll get to that at the end. All right, now we had this idea. Let me just say what our basic tool is. So it's not Riemann's method. We're going to use something else that I still call Riemann's formula. It's a formula that was popularized by André Weil, really written down first by Guinand. And you'll see it's somehow related to moments in a moment. But there's another way of capturing the relation between the zeros of these zeta functions, or say the Riemann zeta function, and the coefficients at the primes. So if I have an L function, any one of the L functions I'm talking about, and I'm assuming Riemann, so the zeros are a half plus I gamma, and the gammas are the zeros. Then if you take a test function, any test function, Schwartz function, for which the Fourier transform is compact support. This is not a self-dual statement. Fourier duality always looks self-dual, but this is not a self-dual statement because I want to be able to evaluate phi in the complex. So phi hat is compact support, even. Then the sum at the gammas of phi, so that's a formula for some expression involving the zeros, is given explicitly, so this is called the explicit formula. It's given by the log of the conductor times phi hat of 0, then a logarithmic integral involving the Archimedean factor, all of which are easy to compute. Here's where the issue is. There's a phi hat at log n over 2 pi, so depending on the support of phi and phi hat, you're going to have some problem of the supports of the function. But anyway, phi hat's compact support, so this, if the support's up to a, then log n over 2 pi would go up to a and would restrict the number of n's in your sum. And the number of n's and the cn's are these, in the elliptic curve case, are the numbers I know how to compute quickly I can compute C and n log n to a power steps for each n. The actual coefficients here are the logarithmic derivative. So I want to explain this because it's going to come back in my main moment problem that I'm leading to right now. And that is, we take the logarithmic derivative of this expression. We're doing some elementary complex analysis. So we take log, differentiate, and then we have a partial fraction expansion. When I take log, the Riemann zeta function has a root number 1. But in general, there's a w here. When I take log and differentiate, I lose that. So I'm going to try to recover that from this formula. Keep that in mind. All right, so our idea for many years, but it took us at least 3 years to realize that there's a conspiracy against us, was simply to write down, treat this as a system of equations for gamma, a system of nonlinear equations for those gammas. Write down many equations, go and ask the machine somehow to solve these equations and get the zeros. And I want to explain that this wasn't so stupid because the density of the number of zeros, so if you have a pi or an elliptic curve of conductor NE, the number of zeros between 0 and 1 will increase, will be basically log of the conductor. And that is exactly why one somehow is getting into the position where one is in log of the conductor steps. Of course, if I want to factor a number, it's the number of digits, not. So it looks kind of promising because there are only few zeros I want to compute, maybe the bottom one and the first few zeros. And so you think you put in a test function, localize it there. But whenever we tried to do something, all algorithms didn't work. And there was a reason, because we finally kind of reduced the problem to something I'm about to show you right now. So the system, you write down systems of equation, and there is some enemy, a couple of enemies that are you fighting against. The problem reduces very cleanly to this problem. So you can forget everything I said. I've got another half hour, and now we're going to talk about polynomials and this underdetermined moment problem. And I think it's a stunningly beautiful problem, and we only have a partial answer to it. So in this application, the log of the conductor of my automorphic form of my elliptic curve, so that's a number of digits basically, will be the size of the matrices that this discussion is about. The problem reduces entirely to the following problem. So forget everything. We have an orthogonal matrix of size 2n plus 1 by 2n plus 1, real orthogonal. Its eigenvalues are all on the circle. That's that. Because it's orthogonal. I look at the characteristic polynomial. It's palindromic because I'm orthogonal. Because I want to emphasize, I don't tell you whether the determinant is 1 or minus 1. That determinant is the root number. I'm going to be trying to guess if the determinant is 1 or minus 1 with some limited amount of data. That's what this problem reduces to completely. So there's, because of the orthogonality, it's orthogonal matrix and the dimension. So, of course, if you're in dimension 2n plus 1, there's an eigenvalue 1 or minus 1 depending on the determinant. And then there could be multiplicities. And here comes the key thing that those system of equations from the explicit formula reduce to, is that we know the traces of the powers of A. So I'm given A. I'll be given A at random. The theory will be such that these conjectures of Katz and mine show that the zeros of L functions behave like random matrices. If they behave like random numbers, we would clean up here. So it turned out that this is why it makes the secret much harder to find, as you will see as I go along. Anyway, right now I'm just setting up the problem. A is an orthogonal matrix. I give you a certain number of traces of powers. So it's just this expression here. I don't know the determinant, but I'm giving you the following SJs of A's for J equals 1 up to K, 0 up to K. And I'm asking you, what can you say about the eigenvalues?
So the A is unknown, but is SJ unknown?
Exactly. And so I'm trying to say, can I recover large information about the eigenvalue? And the problem is a real algebraic problem, real algebraic geometry problem, as you'll see in a second. And precisely because it's real algebraic geometry that we have a chance of saying something interesting. If you take an orthogonal matrix and you know the all but one coefficient and you get a curve, well, then you just don't know where you are on the curve. But the fact that all the zeros are restricted to be on the circle means they can't move very far before they bounce off, and you get very tight estimates on the zeros with an underdetermined problem. So let's see about when it's determined and when it's not. So if k equals n and you know the determinant, then I have there are n, remember the orthogonal matrix was size 2n plus 1. So if I know the determinant, that's one of the eigenvalues. Then I have another 2n unknowns, but they are, because orthogonal, if theta is an eigenvalue, then so is minus theta. So I just have n unknowns if k equals n, and n equations. So it might sound like that sounds dangerous, but of course this is, by the self-reciprocality, if you know the symmetric powers, you know all the symmetric functions. If you know the powers, you know all the symmetric functions, so you know all the coefficients. Just double up, and then just you have the characteristic polynomial. And if you're worried about computing the zeros of a characteristic polynomial, my matrix here never has the eigenvalues. We're in a generic position, so we don't have to worry about high multiplicity. It's not an issue here. So you can recover everything. And remarkably, that is what it should be, because this corresponds exactly to Riemann. So if we're back in the setting where we have complexity, so I'm now in the sub-exponential algorithm, I'll be computing things up to n pi, the conductor to the alpha. Conductor to the 1/2 is exactly where Riemann can compute everything. And in this reduction, and the reduction from our system is exact, k over n is 2 alpha. So if alpha equals 1/2, I have k equals n, and I'm just in a position where I can recover all the coefficients. So it matches exactly. Riemann's gold standard is just saying that if you're given all the coefficients of a polynomial, of the characteristic polynomial of this orthogonal matrix, you can compute the zeros. But we want to go sub-exponential, so we want k over n, or this alpha, to be arbitrarily small. And that's the underdetermined problem, and it's a real algebraic geometry problem. And what we basically are given is this vector y in Rk of moments. And what can we say about the thetas? So this seems like a problem that should have been studied. I don't know why it hasn't been studied. There's one part that will connect to work of Chebyshev, Markov, and Krein. It's connected with moment curves, as you'll see in a second, and I'll raise quickly the main problem right now. But what are we trying to compute? So we have an underdetermined problem. So you might say, you forget it, you can't compute anything. Well, it's not true. You can compute a tremendous amount. So I'm going to let, this is an important definition. So given the, y is the vector of moments in k dimensions. I've got k moments for this matrix. So I let f of y be the forbidden set. This will be a subset of 0 pi. It's an open set. It's the maximal open set such that for any matrix A who's got those moments, it's got no eigenvalues. This is an exact statement. It's got no eigenvalues in this set f of y. The bigger f of y, the more I know. So if k equals n, I can recover all the information. So f of y is the complement of the eigenvalues. And if k is smaller, I want to understand what f of y is. The complement is where the eigenvalues can lie on this level set. So we call that the admissible set. And there is an enemy. So like, this is not a problem where you can actually recover information for every choice of A or every choice of moment vectors. My enemy is a picket fence. If the eigenvalues are exactly in a progression, and I take the moments, all the sums are basically 0. Think of the unitary case. All the way up to, so I learn nothing. I can't learn anything about any eigenvalue or any interval if they are in an arithmetic progression. And so our algorithm is somewhere going to have to look for variations from arithmetic progression, because that's my enemy. So this underdetermined problem cannot be solved if you're exactly on an arithmetic progression. But you aren't on an arithmetic progression because you are in a random matrix situation. And if you were, and now I'll quickly explain this philosophical point that I said, that if the eigenvalues really were coming down randomly, so if you chose a random diagonal matrix rather than a random matrix in SO2n plus 1, then these would be a Poisson process. And in a Poisson process, there are a lot of near coincidences, but there are big gaps. And the gaps are going to be my juice. They're very far from an arithmetic progression, a Poisson process. And that's kind of critical in this analysis. So it's not a worry, it's just that any theorem that I state will be for a typical A, and that's what happens in any application. All right, besides this set, there's another set that is extremely important to us. It's a subset of the forbidden set. It's a set where I can compute the exact number of eigenvalues for any A in the level set. Just given these moments, how many eigenvalues are there in 0 to y? So are there miracle y's in which I can compute the exact number? So any computation when I'm finished is exact. It's a count, it's an integer. And these are the two quantities I want to compute. F of y, the forbidden set, and E of y, the exact count set. And the exact count set is trivially contained in the forbidden set. That's easy to see. And the question is, what can we do if alpha is k over n and allowing alpha to go to 0? All right, so obviously these are moments of powers. These are sums of powers of these eigenvalues. So one can retranslate this to a question about the moment curve, and I'm going to do that now. Originally, we weren't thinking in this language, but later we understood all our algorithms have a beautiful interpretation in terms of this, so I want to explain that. And now I'm in the setting, I think, where everybody should be quite happy, I hope. And maybe you can show me some tricks. I'm really eager to see some new ideas here. All right, so I change variable. Instead of the eigenvalue being theta, I'll make it cosine theta. This makes the eigenvalues near the biggest eigenvalue and smallest eigenvalue squashed a little bit, changes the scale. It's something that I'll return to in a second when I show you some pictures. The moment curve is the following. You take the image of, so the moment curve is this t squared up to t to the k in this notation. I take the image of -1 in r to the k. So this is a twisted curve like this. That's the moment curve. And I'm now going to define the key sets. So akn is the sum of c plus c, so this compact thing in r to the k, n times. So akk is the case where I can recover all the coordinates up to order by solving with Newton's equations for the actual eigenvalues. But if n is bigger than k, remember I'm interested when k over n is small, so k and n are the same k and n, then I'm taking this curve, I'm adding it to itself, Minkowski sum, many times, and I get some weird set. I'm going to show you some pictures of it in a second. And the whole problem reduces to understanding this set, this underdetermined problem. So my basic problem to you guys is, in the Simons Institute of Complexity, is this in P or not, the following problem. I give you k and n is bigger than k, so the n is the number that I give you. I'm asking polynomial in n. Can you tell me whether a given vector is in the set or not? Okay. If you can do that, I can solve my problem very quickly in polynomial time. I can really run with this. So that's, I don't know the answer to this. I tend to think it is in P. But I'm going to show you our algorithms sacrifice, as all algorithms do, and will achieve something nevertheless, but not optimal.
So, but the benchmark would be to get 2 to the n to the alpha or something, epsilon, right? Like,
I would be happy even if you were able to just take akk. So akk, when n is k, I can compute whether I'm in that or not by just this Newton, by finding the roots. Just take that set, which I'm going to show you a picture of, and add it to itself once. So this is n equals 2k. And just tell me whether, in that case, I can tell whether I'm in this set, which is taking the spiky set, convolving it with itself once, very non-convex set, convolving it with itself once, meaning adding it to itself once. And then can you tell if you're in the set or not?
On the previous slide, your problem had a random input because it was a random orthogonal.
Okay, I want you to answer it. For a random guy will be good enough. For random orthogonal, not random. Okay, there will be an issue. If you answered this even for random uniform, I'm also interested. It's a basic question. Yeah, correct. But this question, I think, is a very basic question. Are you in the set? Of course, I'm assuming real numbers and computations can be done to infinite precision. Yeah.
Kn is the sum of the moment curve itself k times. Is that
n times in k dimensions.
N times. So for half of the dimension, you already get the...
No, I've already factored that in.
Okay.
Okay, so k equals n already takes that into account. So k equals n is when n equals k, I can recover everything and say if n is bigger than k, maybe n is 100 times k, then I don't have an algorithm.
What I'm saying, if you add half of the curve was itself half of the dimension.
You mean half of this? And the curve has been, I took cosine and I've unfolded already. So the thing's not symmetric.
Then you get the convex hull.
Yeah, I'm going to get to the convex hull. That's obviously where you're going to make some progress. Correct. But the real problem is what you can do without going to the convex hull, because I'm going to show you there's much more information, obviously. You're losing a lot of information. All right, and why is this relevant? Suppose I want to compute f of y. Suppose I want to see is t, and I have this sum, and I'm saying is t forbidden, meaning there is no summand which has t as an eigenvalue. Then I just have to go through t between -1 and 1. You discretize. Rubinstein has this running beautifully. You discretize. The things are a modulus of continuity, and things work very well. So you discretize. Don't worry about that. You take y minus m of t, and you ask, is this in a k n minus 1? If you know how to do that in polynomial time, then you'll quickly get the forbidden set instantly, or in polynomial time.
Does your a come from the test functions that you're employing?
So the reduction from the real problem to the test functions, that's band-limited functions, cutoffs. The A is eventually the part of the matrix, the sort of...
You're just taking a bunch of measures, right?
You can formulate it as an inverse measure problem with band-limited support, but then there's a way of reducing it to this problem with A now following the fact that the A from number theory will follow the Haar measure on an orthogonal matrix will be only because of my conjectures with cats.
The point is, you're not restricted to randomness.
No, this question, so far, no randomness. My question about whether this is in P has nothing to do with randomness.
You can choose highly non-random constructions.
Yep. So in asking me this is in P.
If this helps you in any way.
No, my interest is only when it's random. And that'll help me. Okay, this is what A3, so the moment curve, if you add it to itself 5 times in dimension 2. At the end, I'll try to show you a picture in dimension 3. It looks like this. If you add this further, it'll just have many more of these.
Color coding.
Okay, the color coding is exactly related to this question. That's the way he did it was he generated points on the moment curve with uniform measure, and then this is a density map. So most points land up in this part, and the central limit theorem says if you add this enough times, this will become a blob, a round blob.
Measure coming from random matrices, or?
No, this is uniform in this picture.
Uniform on the curve?
On the curve. Just uniform on the curve, which is a separate interesting problem. Okay, so you can see that these spikes, which you might want to exploit, which are the non-convex parts, disappear when you start adding many times to itself. And in higher dimensions, it's more complicated. All right, this is the kind of thing that you can see. I just want to illustrate to you. So if you take, maybe this is a good example. Suppose you take k equals 30. So there are 30 eigenvalues here. And this is so if I gave you all 30 moments, I would get all the numbers back. This is giving myself 29 moments, or maybe this is a better picture. If I have 5 eigenvalues.
What is n in this picture?
So n in this case here, k will be 5. There, n is 5, k is 5 in there. I recover everything. N is k is 4. So the forbidden set is the complement here. So this eigenvalue, you know, essentially. This eigenvalue, you know, but those two coalesced. And this is an exact count set. So this is an exact count set, And then you find that when, of course, you have to now do something serious in random matrix theory to see what's going to happen for the random guy here. But if you have just a few less moments, then you do have, this is the real algebraic geometry in action. Imagine I just have one less moment than the number of unknowns. Then you have you start off at a point which you maybe generate, which has all the eigenvalues on a circle. And the two closest eigenvalues will move towards each other if you move in either direction and then bounce off. So the other eigenvalues don't even move, and you essentially know all the others, and that little interval is this interval here, which when n gets large is very accurate. So the real algebraic geometry says that you'll be able to recover all of the eigenvalues if you have k just a little bit less than n. But I'm interested when k over n goes to 0. So k a little bit less than n is not so interesting in terms of what we're trying to do. All right, so this is an example of what those sets look like. And the only way I know to compute these sets of size 30 is when you have the number of moments is 1 less than the total number of unknowns, because then I can run that algorithm by varying t, and I get to AKK, and AKK I know how to solve using Newton. So if I have 1 less, so these are only for j equals 0, 1, 2, meaning in this case there are 30 eigenvalues, and the number of moments 29 and 28. If I get down to 24, this algorithm won't work. And the only algorithm I know is the one I'm about to explain to you now.
You said you have a picture in free space?
Yeah, that's at the end. I'll try. Okay. Because it's 70 pictures. Okay, so our efficient algorithm, of course, convexifies the problem. This is what we were doing without realizing it before. And even though it convexifies a problem, it answers many questions which are way beyond the convex hull. But the first thing you could say is, let's ask whether we're in the convex hull. But before I explain that, I'm going to generalize the problem slightly, because that's relevant in our algorithm. It's an iteration. So instead of having the moment curve plus itself n times, let me take a subset of the moment curve, because at each iteration I will have learned something new. And I'll take the subset of the moment curve. So g is a subset of the interval. G of y came from the previous iteration. I add it to itself n times. I now get a much more complicated set inside r to the k. And I ask about whether I can say, determine whether I'm in that set. Well, in this case, if you allow g to be quite general, then you already are NP complete. So that's because you can make the subset very complicated and reduce down to the sub-sum problem that Karp showed was NP complete. So my hope is that the first step is still in P, and the first step is the most important. I'll return to it. But for our iteration, we need to run this for more general G's, and of course we're not going to face this NP complete problem. We're going to convexify the problem. And that's, of course, the main thing. We relax the problem and ask not whether the point is in the set, but in the convex hull. And then if you just rewrite what it means to be in the convex hull at the first step, you write down a separating hyperplane, you get a linear program, a beautiful linear program that if you're given the moments, which are c in this case, you want to find coefficients b so that you minimize b, and such that the condition that for all t in your set G, I'm doing the second problem, these are inequalities, and you want to minimize this linear functional, so it's just a straight linear program. At step 1, this linear program has a beautiful solution, but on the iterative steps, I don't know how to solve it explicitly. Anyway, we run the linear program, and then there's a second linear program, which is for the exact count, and that is where we try to count the number of eigenvalues in an interval, knowing only these moments. So we try write an upper bound and a lower bound in terms of linear functions. So you have a set of inequalities, which again is a linear program, and then you minimize the upper bound minus the lower bound. So these are, I'll call it linear program 1. Linear program 2 will be part of an iterative process, which is very successful to get there.
These G's are finite sets?
Yeah, these G's are going to be sub-intervals, which you learn at each iteration.
And it's not a linear program, is it? Because the constraint is not a linear constraint.
No, the constraint on the B's is linear for each t.
But you have infinitely many.
Yeah. But that's, you discretize that. It's not a problem.
Semi-definite programming? I mean, there's some very nice Hankel semi-definite programs.
I'll get to this Hankel in a second. But I don't know how to get it to Hankel in... okay, I'll get to that in a second. Okay, so this is a linear program. It's just got infinitely many constraints. That's correct.
In the convexification, does it still tell you anything about the zeta functions?
Oh, yeah. The sub-exponential runs with this. But with this iteration. Yeah.
I'm sorry, I'm going back to the convex hull, but if you add, I think n is the number of iterations, right?
Correct.
Yeah, so if n is k over 2, you're already in the convex hull, right? Because every point in the convex hull is a combination of roughly half of the dimension.
Once I go to the convex hull, it's very easy to describe the set, yes, if that's what you're saying.
No, what I'm saying is that for n equal k over 2,
Yeah.
you're already in the convex hull. The sum of the moment curve with itself is already convex.
No, 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 the sum is never convex.
So every point in the convex hull is a combination.
Now, the convex hull of the set that I call A and K is just the sum of the convex hulls. That's easy.
Right, but every point in the convex hull is a combination of roughly k over 2.
Oh, yes, yes. That's correct.
Yeah, so
Yeah, I'll be using that at step 1. That's a theorem of that's Chebyshev's work. Yeah. It's exactly Chebyshev's work. Yeah. It's called the theory of Chebyshev's weights and nodes. Yeah. Yeah. If we go to the convex hull, you then throw away that these are points, and you really are asking, suppose I have a measure and another measure which has these moments, to what extent, how much do they charge an interval? And this problem for the entire interval was solved ingeniously, brilliantly by Chebyshev. And then Markov gave the, I guess, complete proof. Anyway, you all know what the iteration is. And here, so at step 1, exactly at step 1, the question of whether you're in the convex hull has a, I didn't know this, we found this, and then of course these guys knew this long before us, has a semi-definite description in terms of making Hankel matrices which should be positive semi-definite. So the question whether you're in the convex hull of the set A and K is very easy to answer in terms of semi-definite programming, if it's the whole interval. But if it's a subset of the interval, they have tried, and it's extremely complicated because it gets into very complicated problems about orthogonal polynomials on Riemann surfaces. I don't see any very fast way, and we run a linear program in the second iteration. But for the theoretical understanding of this, we do this at this stage, and this has a very beautiful linear program, semi-definite program. But this is what's relevant to what you're saying, is the second problem of optimizing the difference in the count. Chebyshev solved that in step 1 ingeniously, completely solved that linear program explicitly using Padé approximations and using this theory of nodes and weights which involve half the number of variables. That's exactly correct. And so both of these linear programs, which in general we run a linear program, are run at step 1 using this much cleaner way of checking things. And when you do that, the most important step here is, I should have explained this step. This is the most important step here. When, in our problem, if we have an interval j where the upper bound and the lower bound is less than 1, meaning the upper count and the lower count, which is an integer, lies between two numbers which are less than 1, then I know how many guys there are in there, and that's my exact count. And that's the only reason we, so this is not part and parcel of Chebyshev's work, because there he's looking at arbitrary measures. The minute you look at arbitrary measures, the problem is immediately convexified, because you're taking arbitrary measures and moments. So the problem is just the convex hull problem, and he solves it completely for the interval. But because we are a discrete bunch of points, this is the key new feature, and allows us to iterate and do reasonably well. In fact, well enough to be sub-exponential. So notice that allows me, when I have an interval which I'm trying to count the number of exact number of points, if the linear program ends with this number less than 1, then I get this exact count. And that's what happens in practice. As I said, this is an example. It's with size 30. Ignore the top. Those are more moments than you need. So this, unfortunately, he made it for me yesterday. We had other pictures. This is the forbidden, this small thing is a forbidden set, not the so it's tiny, and we know we can get the whole forbidden set at 30 by using the full, this convexified. This is how much information we lost at 30. So at 30, we know everything. But this is all the information for the forbidden set that we get. However, any piece of forbidden set is going to be good enough for me to get some intervals and to compute the root number. That's the point. And we can go down to 20 here, the forbidden set. This is at the edge where the eigenvalues are squashed, so these intervals are bigger. We can get all the way down to 20. So 30 is not such a big number. The asymptotics that I'm going to use in a minute only kick in slowly. So at 20 already, I told you we could go from 30 to 29 to 28 with the true problem. But look how much we're losing. So this is why I'm really eager to see an improved algorithm, which is not purely based on this convexification and iteration. Because of the iteration, we can answer questions which are not purely convex hull questions, like the root number, but that's a separate question. These are more examples. So let me emphasize here that if at step 1 the forbidden set is empty, we're stuck. And this is where the random comes in. So if we're at step 1, we happen to be the eigenvalues of a matrix which are on a picket fence, we can't learn anything, and we won't be able to learn anything no matter what algorithm we use. But the big thing that we establish is that in the theory of random matrices, this depends heavily on the work of Gordon and Meta. In the theory of random matrices, when these numbers get large, we will always have the forbidden set, if you choose the guide random, be non-trivial and quite big. And so we'll always have a non-trivial forbidden set. And from that, we'll be able to get the exact count for special values, and from that we'll be able to also compute the root number. Why? The root, if I can compute the number of eigenvalues, say between -1 and t and y exactly, then I can tell whether there's an eigenvalue at -1 rather than at 1. That's what the difference is between the determinant being +1 or -1, by just the parity of the number of eigenvalues. So if I actually can break this barrier and the forbidden set, the minute the forbidden set's non-empty, the exact count set comes with it. And what we prove is that when you have complexity going to 0 slowly, we haven't optimized this, then we always can win, and we always get the parity, and we always get the exact count, and that's sort of the main theorem by this algorithm. And it runs and it works very well. It has not been implemented on an elliptic curve, because when n is 30, then the elliptic curve has got 10 to the 30 conductor, and that's a serious undertaking. But Rubinstein is doing that.
How about then choosing a random? Is it
I can't, I don't, what happens is the elliptic curve gives me the random guy. Now there is something that I can do here which is very important, which is why I always dreamt that this will lead to a much better than factoring. And that is, I could take the elliptic curve whose root number I'm trying to compute, and I can twist it, there's some operation, I can twist it by a quadratic character. And when you twist it by a quadratic character, just like I was telling you with the Legendre symbol, the root number changes in a way that you can compute very quickly. And then the conjectures of Katz and myself say that when you go over different quadratic characters, you're sampling in this relative to Haar measure in this orthogonal group. That's been verified. And anyway, this will be the running time. So you now can start sampling, and you just have to have one success after many, many samples, after which you will have computed the root number without ever factoring the number. So you will have computed the parity in this interesting way. So as I say, we're at the level where we're competing with the best factoring algorithms. We're trying to beat that, and that's where this issue comes in. At a practical level, this other P, if the thing is in P, would already improve things dramatically, but I always dreamt that we can go much further. I should say that if I have two elliptic curves or two automorphic forms which have the same APs for P up to log squared, then they actually agree forever. That's a theorem under Riemann. And because of that, what we're trying to compute, it's not completely crazy. All the data is there in the small coefficients. The issue is, can you extract that information out of the data in an efficiently quick way? Yeah. All right. So until recently, my dream was still intact, but Johansson and Lambert have blown away any hope of doing this in polynomial time. And let me explain an absolutely stunning theorem which says that there is no way that you will ever do things that quickly here, precisely because random matrix theory keeps the eigenvalues rigid, and it's keeping this parity question a secret. So let me explain the theorem. Suppose I am in O2n plus 1, and I don't know whether I've got determinant 1 or determinant minus 1. I don't know. I look at this moments in k dimensions, so n and k are as before. I look at the moments, the measure in r to the k, if I were on the determinant 1 component, and the other one is the determinant -1. So both of these are probability distributions. They're variables in r to the k. And all I'm reading are these variables. And I'm trying from those variables to tell whether I'm on this component or that component. I mentioned to you I can sample quickly. So I have a very simple question. What's the total variation between these two measures? If that is not exponentially small, then I win. I mean, I win if you tell me where these two probability distributions are different. And so the point is, I keep on reading this, and I'm reading in the same component all the time. And at what point do I have some statistic that'll tell me I'm on this component rather than that component, and tell me the root numbers are 1 or -1? And I was always hoping that that would go down to something that's far better than factoring. Well, the theorem is, and this is a very strong Tsego limit theorem. For k equals 1, Johansen didn't prove this, and I suspected that when k gets big that his methods won't work, but he's showed they do. These two measures are, so if k equals n to the alpha, if k equals n over 100, we've already know we can do everything. That's this alpha going to 0. But if I want to start to compete with factoring, I want this to be able to go down like, now we're competing exactly with factoring. It's log, cube root of log of the thing, which is measured here by this exponent. So if k, and the 1/3 is exactly the factoring. So if k is n to the 1/3, it proves that the total variation between these two is exponentially small with an exponent which is 2/3. So it shows that you'll never do anything in a polynomial number of steps. These two distributions are close to each other. You cannot distinguish, and you can read as much as you want. You need to make an exponential number of reads in order to tell the difference between them. So no matter what I was doing there or how clever you are with the moment curve, this sets a limit. And the limit is only set because this is random matrix theory. If this were ordinary, this happens very quickly that you can distinguish it too. So this is kind of disappointing that the conjecture of Katz and myself actually is exactly what prevents you from reading this very quickly. But nevertheless, our method is apparently competing. We haven't understood it completely. I think we'll have something which is in the same ballpark as factoring. Never factors the number, computes a root number by this algorithm, and computes more than the root number. And it is, I think, all that you can compute in sub-exponential time. So the main theorem is that you can do this in sub-exponential time. Let me stop. I've gone over. I'll give a picture now. This is A34 from different angles to where you come back to where you started. So when you face it from the one side, it's the A34 in dimension 2, and now he's just moving around the density plot. So it's quite a complicated set. Even there, I'm asking, give me an algorithm to determine whether you're in that set or not. Of course, it's defined, it's a semi-algebraic set, but I don't think you want to start describing in large N what the boundaries are. You should be using somehow the additive structure that it's a Minkowski sum.
But you don't know this surface.
No, I don't understand. Thank you.
So if you do this for random permutations, do you observe larger forbidden sets? Or, I mean, have you tried that? Or do you expect it to be the same?
Yes, if you do it for random diagonal matrices, which I'll take as, so random...
random permutation matrices. So they're...
no, so don't permutation matrices follow... they follow random matrix theory also. It's slightly different. They have longest increasing subsequence, but those all correspond to Tracy Wood. I would imagine that's the same. But if you do random diagonal,
that's completely different.
Completely different, and this works very quickly. And you smash. If the zeros of a zeta function were random Poisson, we would clean up.
Because you get
big gaps. So the interval. Our algorithm is secretly. It finds these intervals where you wait for an interval which has few eigenvalues. If there is such an interval, you find it quickly. And then you use that to get much more information and iterate. But if you don't find such an interval, so you need an unusual event where the mean spacing is a little bit larger by a constant. I know you have a paper with a number of other people here, which is the biggest eigenvalue. That's at a much cruder level than what we're doing here. It's much, much weaker. We're trying to, because we're trying to do an exact count. So the answer, I think, for permutation would be, I think it would be the same as random matrices, because I'm sure things repel each other. So the moral of the story is eigenvalues of a random matrix are very rigid. And this event that you're looking for, which is a big gap, it has to be weighted for a long time. Yeah. On the other hand, if you have a better way of using the... So my main question is this thing in P, and find a better algorithm to search this non-convex set. You saw in the example I gave you at 30, our algorithm, which convexifies, gets a tiny little piece when in fact we know you should be getting everything. That's how much information the convexification loses. But it doesn't lose that much information when n goes large, because we always get a forbidden set and the root number.
And you actually need the forbidden set to contain a large interval, or just to have large measure? No. The forbidden set, the way we're getting it, always is an interval. And the bigger the interval, the lower the complexity you can deal with. I mean, that's kind of clear intuitively, because you can make a function of low degree, a polynomial of low degree, which will approximate the characteristic function. By the way, Chebyshev's algorithms with Padé approximations in the first step to find that minimization problem is just stunning. It uses, as he says, it uses half the number of variables in a clever way, and then the Padé approximate gives it to you instantly. So the measure problem is, the convex problem is easy, but this is about the set. Yeah.